Welcome to Study Loop.
So this question deals with wavelength and frequency and the relationship to energy. So over here in this box, we have a couple of equations we're going to need to use. Energy is related to um, frequency times Planck's constant. So I've supplied Planck's constant here as the 6.63 times 10 to the negative 34 joule seconds. And wavelength and frequency are related by the speed of light. And I've supplied that number here. Now, this is the information that we were supplied with, that for a mole of carbon-carbon bonds, 348 kilojoules of energy is required to break the bonds for every mole of carbon-carbon bonds we have. Well, the units that we're going to be utilizing in ultimately determining the frequency and wavelength associated with that energy is joules. So I've just rewritten that for 348 kilojoules as 348,000 joules per mole. Well, here's what we know. That gives us the energy associated with the mole of carbon-carbon bonds, but we want to look at an individual carbon-carbon bond. And so what's in a mole? Avogadro's number. So every mole of carbon-carbon bonds contains this many 6 times 0, 2 times 10 to the 23rd carbon-carbon bonds. So if we rewrite that for an individual bond, we get this much energy associated with an individual bond. That's the energy. Um, Ignore this down here. That's just some extra information that we won't be needing. But that's the energy that we're going to use then to determine the frequency of the light needed to break a carbon-carbon bond. So let's start with that. Plug in that energy value, Planck's constant, and let's determine the frequency of the light. And when we rearrange the numbers, we find that the frequency is this 8.7 times 10 to the 14th. Hertz or inverse seconds, they're used interchangeably. That's the frequency of the light. We're asked to determine the wavelength of the light associated with this process. Well, let's use the other equation then. Speed of light relates the wavelength times the frequency. Speed of light is 3 times 10 to the 8th meters per second. Frequency, we just determined from the number above, plug that in. And again, when we rearrange the numbers and solve for wavelength here, we find that in terms of meters, remember those are the units of length used in the speed of light. In terms of meters, that's 3.44 times 10 to the negative 7 meters. It's usually more beneficial when we're talking about really small measurements um, like those of wavelength to talk about that in terms of nanometers. So the final step then is just to take those meters, knowing that there's 10 to the ninth nanometers for every meter, convert it to nanometers. That ends up being 344 nanometers. This is our ultimate answer here. Would be then the wavelength, or the minimum wavelength uh, needed, or as they put it, the longest wavelength needed to supply the energy associated with breaking an individual carbon-carbon bond.